Hi, so in this video, I'm going to cover operators in Java, and operators are just functions you can use to interact with numbers and also do logic. They're really important and helpful. And to start, I'll use these numbers, x equals 7, y equals 8, and z is a double 3. First up, we have your basic math functions, addition, subtraction, multiplication, division. So like if I said int outcome equals x plus y, and then I print that, we get in the bottom here on the console 15. It adds them up. Subtraction works as well. Now for multiplication, you use an asterisk. And for division, you use a slash. An important thing to note for division here is that I'm using two integers, 7 and 8, and they don't divide perfectly. But if I run this, I'll get 0. Because when you do integer division, when I set it to an int here, and when I use two integers as the numbers, then integer division takes whatever the outcome is, like 7 over 8 is 0.875, and it just deletes all the decimal places. So this basically integer division always rounds down. 0.875 rounds to 0, like that. But if I set this to a double, and I use z for instance here, now, and that happens whenever these two numbers are integers, but now that I have a double with a decimal in the division, Java will treat it as division with decimal places and actually save all your decimal places. So that's your kind of first basic math operators. Something else to note with the plus addition one is that this can also be used with strings. So if I said string outcome equals I plus by, and I ran that, now we get, so that's string concatenation where it attaches two strings, one at the end of the other. So the plus for numbers adds them together like math, and if for strings, it will combine the two of them next to each other. Now if I clear these, the next thing, still kind of math operators, are modulus, which uses this percent sign. And the way modulus works is if I do int outcome equals y mod 7, or y mod x, sorry. This says 8 divided by 7 uses up 1 dot dot dot, because there's numbers afterward. And then it says, what's the remainder? So the remainder in this case is 1. And so y mod x would output 1 because it outputs the remainder. Now if I had y as 18, it would say 18 divided by 7 is 2 with some numbers, and then the remainder in this case is 4 because 18 is 14 plus 4. And just to check here, because 8 mod 7 is 1 because 8 divided by 7 has a remainder of 1. And this you can use for things like checking if something is a multiple of 3 by giving you mod 0, or check if it's even or odd by taking mod 2, and if it's 0 then it's even, or if it's odd then it's 1. The other things you can do here are these plus and minus operators do +1 and -1. So if I said x plus, and then I print x, so x up here is 7, and then I do x plus, and it will add 1, and that will give me 8. Similarly, if I did x minus, you'll get 7, or sorry, 6, because it started as 7. Now you do a minus, and it's 6. And that kind of wraps up the math operators, but you have addition, subtraction, multiplication, division, and then modulus, which is remainder, and plus and minus by increments of 1. So next up we have assignment operators, which are all based around this equal sign being an assignment thing, which you're probably familiar with. If I want to set x to 10, even though it was 7 earlier, I would just do this. And like if I wanted to create a variable, declare it to be something, again, you use the equals operator for assignment. Now, if I want to take this and the equals combines with your arithmetic operators. So if I want to add 3 to my x, instead of saying x equals x plus 3, I can just do x plus equals 3, print x, and now we get 10. This also works for minus equals, asterisk equals. Asterisk equals will give you 21 because we're doing multiplication, and it's setting x to this new value each time. Now, if we do division equals with x here, because x is an integer, as declared up top, you get integer division. 7/3 is 2 1/3, but it wipes out everything after the 2. So x/3 gives you 2. If you did this with z now, and then we print z, we get 1.0. And that's because z is a double. So when you do division with the double, it saves it again as a double, and we print it. You can also do this with variables, like if I did z / equals x, it does z divided by x and saves the value. But if I switch this to say like x divided by z, it will give me a whole, number because x is an integer. So this first number is what you're actually setting. Sorry, I didn't change the output there. So here we get 2 because even though z is a double, you're saving it to this x value, which is an integer, so it wipes away everything afterward. And finally, you can also do modulus operators. So x mod 4 is 7 mod 4. 7 divided by 4 gives you a remainder of 3, so that's where you get. So this is a shortcut for doing math operators and just changing the values of these numbers. So now we move from these standard arithmetic operators to bitwise operators, which still use numbers, but now we use their binary outputs. So I've changed x and y now to 3 and 5. And 3 in binary has 1 times 2 to the 0, so it has 1, 1 plus 1, 2, and then no 4s or 8s, so we get 0, 0, 1, 1. 5 is a 4 plus a 1, so it's represented as 0, 1, 0, 1. Now, if you do A and B, int outcome equals A and B. And then, sorry, not A and B, X and Y. And then we run this, we get 1. And how does that work? So if we come back up here, and I lay over 3 is 0, 0, 1, 1, and 5 equals 0, 1, 0, 1. So now when you do the AND operator, it compares each bit. So this one and this one, they're both zeros. So what it counts as the output here is a 0. Because AND needs both numbers to be 1s or ONs to count. Now here there's a 1 in the 5 for the 4 slot, but there's no 1 in the 4 slot for 3. Like 3 doesn't have any 4 digits. So this is also a 0 because it needs both of them. It checks is this and this on. Again, in the 2 slot, 3 has a 2, but 5 doesn't have a 2. So this is a 0. And then you get to the end, you get both 3 and 5 have a 1 in this 1 slot. So you come out with a 1. And 0, 0, 0, 1 is 2. So when you print outcome, you get 2. Now if I go back, so that's the AND operator, and it gives you a number, but it's based on the bits of the numbers you used. Now if I do x and y, if I do x or y, and or uses this symbol above the backslash vertical line. Now or cares is either one on. So it'll go through and say a 0 and a 0, that's nothing. But here there is a 1. Here there's nothing, but here there's a 1, so I'll still take it, whereas the AND needs both of them to work. And then for 3 and for the 2's digit, again, there's a 1 here, so you'll get a 1. And then when they're both on, that's still good. So we get 0, 1, 1, 1. And 0, 1, 1, 1 is 7. So you get 7 down here. Next up, for bitwise operators, you have you use a caret, which stands as an XOR. An XOR is like an OR, except when they're both on. So here, 0 and 0, that's nothing. 0 and 1, well, that's something, that's a 1. 0 and 1 again, that's something, that's a 1. But with an XOR, it's like an anti-AND OR. So when you have one or the other, it counts it. When you have neither, it doesn't. But if both are on, they cancel out and turn off. XOR asks, is only one of these two on? Whereas if they're the same, like 1s or 0s, you get a 0. And that, you have something in the 2's and the 4's, so that equals 6. So if you take 3 and 5, here they're bit, you combine it with XOR, and you get 6. So AND is, they both have to be working, OR is any of them, XOR is one of them but not the other. Next we have this tilde bitwise operator, which is a bitwise complement one. And for this, I'm just going to start with something like 3. What this does is it gives the complement, so it reverses all the digits. So 0, and what you can really think of it as however many number of 1s, and there's a 0 in front of it, which tells the computer it's a positive number. So when you flip it, you get 1, 0, 0, and then Java reads this as a 2's complement number, which means there's this 1 in front, and it treats it as a negative number. So this 1 is in the 4 spot, it's a negative 4. And that's what we'll see doing this. And then if I ran it with like the 5, which is 0, 1, 0, 1, we'll get 1, 0, 1, 0. Sorry, this should be 5 now. 1, 0, 1, 0. And now this is in the 8 spot, so that's a negative 8. And this is in the 2 spot, so this first number is negative, everything else is added. Negative 8 plus 2, negative 6. So this operator will flip the bits and then turn it into a 2's complement negative number. And really what you'll see is any number you put in here, so if you say tilde n equals, it'll come out as a negative number of n plus 1. So 8 becomes negative 9, 5 becomes negative 6, 16 becomes negative 17, etc. The next two are these shift left and right operators. So I'll stick with 5, I guess. And if we do 5 equals 101, or 0101, then when you shift it right, you do whatever number you're starting with, this shifts the thing, and then a number, so 2. And I'll start with the shift left, and what that does is it shifts all of these zeros and ones 2 to the left, so you get 1, 0, 1, 0, 0, because we've added these 2 spaces on the left, on the right, I mean. Or if you have, 7, 1, 1, 1, then you'll end up with 1, 1, 1, 0, 0. So 7 shift left 2 is 28. And because this is base 2, every time you shift it to the left one, you're multiplying it by 2 really. So shifting it left 2 is the same as times 2 times 2 or times 4. That's why you get 7 to 28. If you had 8 shift 2 twice, you would end up with 32. And if you did it a third time, so if you had 8 and a 3, it would be 8 times 2 to the third is 8. So 8 times 8 would give you 64. Now, sticking with 8, which is that, if I do shift right, it does the same thing as shift left, but as you can guess, it moves everything right. So this would be shift it right 3, and you just get 1, which is this 1 down here. We had, 12, shift right 2, 8, 4, then we would end up with shift everything right twice, and you get like this. You'll end up with this 3. So shifting right divides everything by 2. So do it twice, you're 12 divided by 3. And the final thing is, if you have a shift right with a third greater than sign, this tells it to fill the empty spaces with zeros. So the outcome will be about the same, but if you want to use this, outcome variable and do more bitwise calculations, then you can tell it to shift right and it'll fill the spaces with zeros rather than compressing. Just like the math arithmetic operators, the bitwise operators have equals versions. So if I have x up here is 3, and I said x and equals y, and then I told it to print x, well, x and y is, remember, 3, 0, 0, 1, or 0, 1, 1. 5 is 1, 0, 1. So x and y would be 0, 0, 1. And this is if you want to just change the value of x efficiently and not use another variable, you do this and equals. Same thing if you say like x left equal 2, that'll give you x was originally that, so it'll shift it left 2 and you'll get 1, 0, 1, 0, 0, or x times 2 times 2, 12. So these are your quick assigns. You can do the same thing with right shift or equals, or the XOR equals. And they all use the same property says up here, but now you're assigning it back to x without having to write out like x equals x or y. So this is the same as x equals x caret 2. And finally, we have these logic operators, which are used for Booleans. So if I said Boolean both equals, and now I'll say something like x. Okay, well first, the first operator to know is the double equals. A single equals, like if I said x equals 7, is a assignment, but a double equals is like x equals 3. That checks if x equals 3. And I can say, and that's a Boolean value, so I can save that as Boolean 3 equals x equals 3. So if x does equal 3, that'll be true. And if x doesn't equal 3, it'll be false. Or now, if x equals 5, 3 will be true. Which is a weird sentence. So all of these logic operators are Boolean operators. So you can see x is 3, so x equals 3 is true. But if I said y equals 3, and then we run that, y is 5, so this gives us false. And these are the things you're going to use for like if and while statements. Now if I wanted to change this, the other thing you can, the next operators are the AND operator, which checks that two Booleans are both true. So I could say here x equals 3, which would give me true, and y equals 3, which would give me false. And I'm saving it back to this 3 Boolean. This will give us false, because one of them is true, but one of them is false, and they have to both be true for this AND to work. So this AND says, are the two values both true? And if they're both false, it'll also both be false. Now, in logical gates, these two dashes aren't XORs, they're just ORs. So this, when I run this, will give me true, because y equals 3 is false, but x equals 3 is true. Equals, I should say. X is 3. So as long as one of these two is right, the whole statement will return as true. And the final thing to check, to cover here, is the exclamation mark. So exclamation mark would be something like, I can say not. Exclamation mark means not in programming. So if I put the exclamation mark in front of the equals, this says x is not equal to 3. So since x is equal to 3, checking if it's not will return false. Whereas checking if it's not equal to 5 will give me true. So this is just checking, is x not 5, or is x not 3? The other thing you can do is down here. This, as you can see, will give me 3 is true, but I can say 3 equals not 3. And that will, this gives false because the exclamation mark basically reverses whatever Boolean it was. 3 was true, so now 3 is going to be false. If 3 was false, 3 not 3 is true. And that covers all of the Boolean operators, Boolean logic operators for Java.